As the globe rejoins in relief over the 3-week atlas, humanity's third deep space voyager, a more disquieting event is silently unfolding, and we've only just caught wind of it. A comet, exhibiting remarkable bursts of activity, is charting a course perilously close to our planet's trajectory. It evaded our observational network, a silent spectre, until the sun's brilliant glare inadvertently revealed its presence. On October 21st, 2025, a mere 8 days hence, it will achieve its nearest point to Earth. What does this portend for us? Is this the genuine peril? Stay with me until the conclusion, and you will grasp why the true threat was never the celestial body gracing the headlines, but the one we almost overlooked. If these enigmas have captivated you as they have me, be sure to activate the like button and subscribe, ensuring you remain abreast of every development as this narrative unfolds in real time. Share your location in the comments, along with the current time there, and voice your thoughts on whether we are privy to the complete narrative surrounding these epoch-making discoveries. And if you wish to contribute to the expansion of this community, please disseminate this video across X, Facebook, Reddit, or even within your personal messaging groups. Your support is the bedrock upon which we continue to pursue stories of this magnitude. Thus, our profound gratitude for your steadfast backing. Part 1. The focus of current discourse. The entirety of attention is fixed upon 3 Atlas. The media proclaims it as enigmatic. Social platforms are abuzz with speculation, while astronomers endeavour to pacify us with assurances of its harmlessness. Their pronouncements are accurate. 3 Atlas, that cosmic sojourner originating from beyond our immediate stellar vicinity, will traverse Earth's orbital sphere at a comfortable distance of 1.8 astronomical units, approximating 167 million kilometers. NASA has articulated its position with clarity: zero threat. Its orbital path remains distant, a celestial observer destined to glide past and recede into the vast unknown. So, what fuels our fascination? It is its extraterrestrial origin. The very term interstellar imbues it with an allure that eclipses practical considerations. We are drawn to the exotic visitor, the unfamiliar presence. In doing so, we neglect to scrutinize those already within our domain. While the world's gaze is fixed upon 3 Atlas, another entity is stealthily entering our cosmic neighborhood. Comet C2025R2, christened Swan, after the instrument instrumental in its discovery, is rapidly approaching. On October 21st, 2025, just 8 days from now, it will reach its closest proximity to Earth. Not 1.8 astronomical units, nor even 0.2606 astronomical units, a distance of approximately 39 million kilometers. This is far closer than one might imagine. This is closer than we are typically comfortable with for uninvited entities. Allow me to elucidate the nature of this phenomenon. R2 was identified in late September 2025 by an amateur astronomer named Vladimir Bezugi, who was meticulously analyzing data from a solar wind monitoring instrument aboard the SOHO spacecraft. His method involved no telescopic observation. Rather, he was observing the emission of hydrogen in ultraviolet light. This is an unconventional approach to comet detection. Typically, ground-based optical surveys meticulously scan the heavens, identifying faint points of light reflecting solar radiation. However, R2 remained undetected by these methods. It had been concealed within the sun's glare, its angular separation from the sun too small for terrestrial telescopes to resolve. This phenomenon is referred to as the Hulish or Hulichek blind spot effect. Objects situated within this region are effectively spectral, existing but imperceptible until they emerge into clearer view. R2 only became visible after it had already passed its perihelion, its closest approach to the Sun, on September the 12th, 2025. By the time of its detection, it was already commencing its outward journey, heading in our direction. Its perihelion distance was approximately 0.5 astronomical units, roughly 75 million kilometers from the Sun. This proximity is sufficient to vaporize volatile substances from its surface, triggering outbursts and potentially destabilizing its structure. Indeed, this is precisely what transpired. In late September, observers documented a sudden surge in luminosity. The comet's magnitude escalated to approximately 5.9 or 5.6, depending on the specific report. Its coma, the diffuse envelope of gas and dust enveloping the nucleus, expanded considerably. Photographic evidence revealed a greenish luminescence, a characteristic signature of diatomic carbon and cyanogen radicals fluorescing under solar ultraviolet radiation. Its tail extended across several degrees of the sky, discernible through binoculars for those with precise knowledge of its location. However, a critical aspect remains unknown. We are still unaware of the nucleus's dimensions. Its rotational state is also undetermined. We cannot ascertain if it has undergone fracturing or if such an event is imminent. Comets are inherently volatile celestial bodies. They possess the propensity to shed fragments, disintegrate into multiple pieces, and disseminate trails of debris along their orbital paths. Should R2 undergo any such transformation, these fragments would deviate marginally from the parent comet's trajectory. They would disperse, creating a wider field of potential intersections with Earth's orbital path. The minimum orbital intersection distance, or MOD, between R2 and Earth is approximately 0.048 astronomical units. This equates to roughly 7 million kilometers. In the grand scale of the cosmos, this represents an infinitesimally small gap. It is the boundary between safety and potential peril, contingent upon subsequent events. I am not here to assert that R2 is destined to impact Earth. Current orbital projections indicate this is not the case. However, I am here to highlight that our inability to detect it sooner constitutes the paramount risk. We have engineered a detection apparatus that functions with remarkable efficacy for celestial bodies situated in opportune celestial positions, possessing sufficient luminosity and observable at propitious moments. Yet, if an object eludes detection by remaining within the sun's glare, or arrives from an unexpected vector, or undergoes a sudden luminosity increase after our observational efforts have ceased, we risk missing it entirely. We overlooked R2 until it was virtually upon us. How many others have entirely escaped our notice? This discourse is not intended to incite panic. Panic is unproductive. Its purpose is to draw attention to phenomena that consistently elude our observational purview. It is about acknowledging that the most formidable entities are not those featured in sensationalized headlines, but rather those that remain unseen until it is too late. 3 Atlas serves as a diversion, akin to a magician's misdirection, drawing our focus while the true event transpires elsewhere. R2 is the actual event. Therefore, our approach will be threefold. Firstly, we will deconstruct the distraction presented by 3 Atlas and demonstrate its inherent safety. Secondly, we will delve into all known and unknown aspects of R2. We will explore hypothetical risk scenarios, including dust trails, fragmented debris, and meteoroid swarms. We will draw parallels with past near misses that were detected with minimal warning, objects that narrowly bypassed our protective systems with mere days or hours of prior notice. Finally, we will delineate what demands your attention, what you should expect from the institutions tasked with monitoring these phenomena, and the implications of the inevitable failures within our detection network, which occur more frequently than commonly perceived. And when such a failure transpires, the entity that infiltrates our awareness is not always the one we were expecting. Part 2. The Mechanics of Discovery. Why did SWAN detect it, while ground surveys did not? Comets are typically identified through optical sky surveys. Telescopes systematically scan the night sky, searching for faint points of light that exhibit movement against the backdrop of stars. As these celestial bodies approach the sun, their luminosity increases due to the sublimation of ice, resulting in the formation of tails. This methodology has been employed for centuries and is generally reliable, with notable exceptions. Comet C2025R2 was not discovered by an optical telescope. Its identification was achieved through a hydrogen emission detector housed aboard a spacecraft orbiting the Sun. The instrument in question is known as SWAN, an acronym for Solar Wind Anisotropies. It is an integral component of the SOHO mission, the Solar and Heliospheric Observatory, which was launched in 1995. SWAN was engineered to capture images of the solar wind by detecting hydrogen Lyman alpha emissions within the ultraviolet spectrum. Hydrogen exhibits fluorescence at a specific wavelength, 12 1.6 nanometers, which is invisible to the human eye but prominent in ultraviolet light. When comets release water vapor through sublimation, this vapor dissociates into hydrogen and oxygen. The hydrogen then disperses to form an extensive cloud surrounding the comet, far exceeding the dimensions of its visible coma. SWAN possesses the capability to detect this cloud from millions of kilometers away, even when optical telescopes register nothing. This is not an unprecedented discovery method. SOHO SWAN has been credited with the discovery of thousands of comets throughout its operational lifespan. The majority of these have been small, sun-grazing objects that subsequently vaporize upon entering the solar atmosphere. However, R2 is not a sun grazer. It is a visitor from the outer solar system, presumably originating from the Oort cloud, embarking on a close solar pass before returning to its distant origins. The factor that rendered it undetectable by ground-based surveys was its spatial orientation. It was situated too proximate to the Sun in the sky, resulting in an insufficient angular separation. Telescopes located on Earth are incapable of directly observing the Sun without sustaining damage. A specific region encircling the Sun, a cone of invisibility, exists wherein celestial objects are completely obscured from our view. Astronomers refer to this as the Hulich effect or the Hulichek blind spot, with attribution varying based on historical preference. The underlying principle remains consistent. Objects within this zone are effectively phantom entities. R2 traversed this zone during its perihelion passage. It executed a solar orbit on September 12, 2025, at a distance of approximately 0.5 astronomical units, equivalent to 75 million kilometers. For several weeks preceding and following this event, it remained imperceptible to optical surveys. By the time it emerged from the Sun's glare, it had already passed its perihelion and was proceeding outward towards Earth's vicinity. It was at this juncture that Vladimir Bazougi, an amateur astronomer, identified it within the SWAN data. He was meticulously reviewing archived ultraviolet imagery, searching for the characteristic glow of hydrogen. He discovered a diffuse cloud exhibiting movement, a nebulous entity whose position shifted over time. He meticulously logged his observation. Subsequent investigations by other observers confirmed his findings. The comet was indeed a genuine celestial body. However, by this point, weeks of crucial observational time had been lost. We lacked any data pertaining to its pre-perihelion behavior. We were ignorant of its luminosity progression, the evolution of its orbital path, or whether it had already commenced fragmenting. Detection bias operates as a formidable impediment. Optical surveys are subject to minimum magnitude thresholds, lacunae in sky coverage, meteorological disruptions, and the inherent limitations imposed by solar glare. Instruments designed to detect hydrogen emissions in the ultraviolet spectrum, such as SWAN, possess distinct sensitivities and their own unique blind spots. They are capable of detecting comets that elude optical telescopes, but they are not engineered for comprehensive sky mapping. They function as specialized instruments, consequently identifying specialized phenomena. The ramifications of delayed detection are significant. Orbital uncertainties are exacerbated when observational data is limited. Extended periods of observation are requisite for refining trajectory calculations, quantifying gravitational perturbations, and accounting for non-gravitational forces such as outgassing. R2 was identified at a late stage, resulting in an imprecise orbital determination. Even now, weeks later, residual margins of error persist. While its general trajectory is discernible, general is not synonymous with precise. In the realm of orbital mechanics, precision is paramount. Furthermore, we were deprived of observing its initial activity. Comets frequently experience outbursts in close proximity to the Sun when solar heating triggers the explosive release of volatile compounds. If R2 underwent such an event, it escaped our observation. We are uncertain whether it shed substantial fragments during this period. We lack knowledge regarding potential nucleus fracturing. Its rotational state remains unknown, influencing its spin and wobble under the influence of asymmetrical outgassing forces. All of this vital information is irretrievably lost. We are navigating blindfolded in an attempt to predict the behavior of an object whose performance we only began observing midway through its spectacle. This situation does not represent a failure on the part of individual astronomers. Rather, it signifies a systemic deficiency within our detection infrastructure. Our observational protocols have been optimized for specific types of celestial bodies situated in particular regions of the sky. When an object deviates from these parameters, it is missed, and potentially entirely missed, until an amateur astronomer, granted access to sophisticated spacecraft instrumentation, serendipitously identifies a hydrogen emission in archived data. How many other comets have escaped our detection? How many are presently traversing the solar system, rendered invisible due to their presence in an unfavourable location, or observed at an inopportune moment? We possess no definitive answer. Such uncertainty is precisely the crux of the problem. In the subsequent segment, we will scrutinise the actual observed behaviour of R2 since its discovery, including its outbursts, anomalies, and structural peculiarities, which collectively elevate this comet beyond the status of a mere icy celestial body. Part 3. The observed actions of R2. Allow me to guide you through the chronological sequence of events. On September 11, 2025, Vladimir Bouzouki identified a mobile hydrogen emission source within the SWAN imagery. The object was officially designated C20-25R2, with the designation R signifying the second half of the month of discovery, and the numeral 2 indicating it was the second comet identified during that period. Optical verification was swiftly obtained. Ground-based observers directed their telescopes towards the specified coordinates and confirmed its presence. A faint, nebulous patch, a coma emitting a subtle glow in the pre-dawn sky. The comet had completed its perihelion passage the preceding day, on September 12th, at a solar proximity of approximately 0.50347 astronomical units. This distance is remarkably close. It is sufficiently proximate to facilitate the sublimation of water ice, carbon dioxide, methane and ammonia, all the volatile compounds typically carried by comets. It is close enough to precipitate activity. And activity indeed occurred in late September. Observers reported a sudden augmentation in its brightness. The comet's apparent magnitude increased significantly. Some estimates placed it at 5.9, while others indicated 5.6. Magnitude is a logarithmic scale, meaning even a minor numerical alteration signifies a substantial increase in luminosity. The coma visibly expanded. Photographic records depicted a distinct greenish halo surrounding the nucleus, a phenomenon attributed to the fluorescence of diatomic carbon molecules under ultraviolet radiation. This characteristic is commonly observed in comets. Carbon compounds sublimate from the nucleus, become ionized by solar radiation, and consequently emit a green light. While appearing extraterrestrial, it is a straightforward chemical process. The comet's tail exhibited asymmetry. Certain images displayed distinct streamers, narrow jets of material emanating outwards, away from the Sun. This observation suggests localized outgassing, likely originating from active fissures on the nucleus's surface. Comets are not uniform bodies. They comprise a heterogeneous mixture of ice and rock, with certain regions possessing a higher concentration of volatile materials than others. As the nucleus rotates, different fissures become exposed to solar radiation, thereby triggering bursts of activity. The resultant effect is a tail that dynamically alters its shape, pulsates, and occasionally bifurcates into multiple streams. R2 demonstrated all these characteristics. Observers also noted a significant retention of dust. Ordinarily, solar radiation pressure disperses fine dust particles away from the comet, forming a smooth tail. However, if the dust particles are of substantial size or possess adhesive properties, they lag behind, creating a diffuse cloud that expands gradually. R2 appeared to be generating a considerable quantity of large dust particles. This observation carries significant implications. The presence of large dust particles suggests that the nucleus is shedding substantial material, potentially including fragments or portions of its surface fracturing under thermal stress. If these fragments are sufficiently large, they might persist as independent entities, each following its own trajectory. These trajectories could diverge from that of the parent comet, thereby propagating a debris field across interstellar space. A particularly striking image surfaced on the Astronomy Picture of the Day website on September 18, 2025. It showcased R2's greenish coma silhouetted against the twilight sky, with its tail extending upwards, away from the overwhelming glare of the obscured sun. At this point, the comet remained close to the horizon, posing observational challenges, yet it was unmistakably visible. Astrophotographers managed to capture its image, some utilizing binoculars, others employing small telescopes. Reports describe the tail as extending several degrees in length, a spectral ribbon unfurling across the celestial expanse. However, a crucial caveat exists. Brightness predictions for comets are notoriously unreliable. Comets do not adhere to predictable patterns. They experience sudden outbursts, their luminosity can diminish, and they are prone to fragmentation. Their brightness is contingent upon the extent of surface area undergoing active sublimation, which in turn is influenced by the nucleus's size, composition, rotational state, and the intensity of solar heating. While we can formulate educated estimations, comets possess a remarkable capacity for surprising us. R2 was predicted to reach a magnitude of 4 under optimal conditions, which would render it readily visible to the naked eye from a location with minimal light pollution. Alternative predictions are more conservative, suggesting it will remain around magnitude 6, necessitating the use of binoculars. As of October 10, 2025, its reported magnitude stands at approximately 6.7, placing it just beyond naked eye visibility. Whether its luminosity will further increase is contingent upon additional outbursts, a possibility about which we remain uncertain. The nucleus itself remains unresolved. Telescopes can only discern the coma, the luminous envelope of gas and dust. The solid core remains concealed within, too diminutive and faint to be distinguished. Its precise dimensions are unknown. Estimates derived from its luminosity and observed activity suggest a diameter on the order of a few kilometers, but this remains speculative. Its shape is also undetermined. It is uncertain whether it constitutes a singular entity or a loosely aggregated cluster of fragments. We cannot ascertain if it has already undergone fragmentation. Some comets fracture subtly, shedding components without dramatic outbursts. These events are only discernible retrospectively through high-resolution imaging of the coma, revealing multiple condensed nuclei. While speculative, this possibility warrants consideration. The outburst observed in late September suggests the presence of internal volatile reservoirs. Internal pressure within the comet likely built up and was subsequently released with explosive force. This could be attributed to carbon monoxide ice undergoing rapid sublimation, or perhaps subsurface pockets of water ice suddenly exposed to solar radiation. It could also be a structural failure, a fissure opening and venting gases. Regardless of the precise mechanism, it occurred once. It could recur. And should such an event coincide with the comet's proximity to Earth, the resulting fragments would disperse to form a debris cloud, a cloud through which we might potentially traverse. Next, we will examine the quantitative data, the precise orbital parameters, distances, velocities, and geometric configurations that determine whether this phenomenon warrants mere curiosity or genuine concern. Part 4. Quantitative data and a reality check of the orbit. Allow me to present the geometric configuration. Comet C2025 R2 follows an orbital path around the Sun that is nearly parabolic. Its orbital eccentricity measures 0.9993699, a value exceedingly close to 1, implying an open trajectory. An eccentricity precisely equal to 1 signifies a parabola, an open curve wherein an object originates from an infinite distance and returns to infinity. An eccentricity marginally less than 1 indicates an exceptionally elongated ellipse, an orbital path that necessitates tens of thousands of years for completion. R2's orbit possesses a semi-major axis of approximately 798 astronomical units. This signifies that its aphelion, the farthest point in its orbit, is situated far beyond the Kuiper belt, deep within the Oort cloud. The estimated orbital period is 22,554 years. This comet last visited the inner solar system during the late Paleolithic era, a period marked by early human cave art and mammoth hunting. The inclination of its orbit is approximately 4.4747 degrees. This represents the angle between the comet's orbital plane and the ecliptic, which is the plane of Earth's orbit. 4.47 degrees is a relatively low inclination. The majority of comets originating from the Oort cloud arrive at steep inclinations, descending from random angles. R2, conversely, is nearly coplanar with the planets. This characteristic simplifies the prediction of its trajectory, but also means it spends a greater duration within the ecliptic plane, where Earth orbits. This proximity elevates the probability of close encounters. Perihelion, its closest approach to the Sun, occurred on September 12, 2025, at a distance of 0.50347 astronomical units. This equates to approximately 75 million kilometers, positioned just inside Venus's orbital path. At this proximity, solar heating is exceptionally intense. Surface temperatures can ascend to several hundred degrees Celsius. Water ice undergoes rapid sublimation, and volatile compounds are vigorously outgassed. During this phase, comets achieve their peak luminosity, becoming spectacular celestial displays, but also inherently unstable. We now shift our focus outward. R2 is receding from the Sun, but its trajectory intersects with Earth's orbital path. On October 21, 2025, the comet will achieve its closest approach to Earth. The distance will be 0.26065 astronomical units, translating to approximately 38,925,117 kilometers. This distance is roughly 100 times the distance to the Moon. While this may sound considerable in human terms, it represents a near miss on a cosmic scale. However, the critical metric is the MEOD, the minimum orbital intersection distance. This figure represents the smallest conceivable gap between Earth's orbit and the comet's orbit, calculated geometrically without regard to temporal synchronization. For R2, the MOD is approximately 0.048 astronomical units, roughly 7 million kilometers. In essence, if one were to plot both orbital paths in three-dimensional space and measure the shortest distance between them, the result would be 7 million kilometers. This is the separation. If the comet and Earth were positioned at discordant points in their orbits, this gap could theoretically diminish to zero. However, this is not the case. The current orbital solution indicates that on October 20th, Earth and R2 will be separated by 39 million kilometers. The comet will pass, and we will remain safe. The models corroborate this prediction, and the calculations support it. NASA is not issuing any warnings. There is no alert indicating an impending impact. So, why does this discussion persist? Because orbital solutions are inherently imprecise. They are derived from observational data, and observational data is subject to uncertainties. The more data points you acquire, the more robust the conclusion becomes, yet R2's discovery was delayed. Our collection of observations is less extensive than ideal. While the orbital path is reasonably well defined, it lacks absolute precision. Minor gravitational influences, non-gravitational forces stemming from outgassing, alterations in the comet's rotational state or mass distribution, any of these factors can subtly redirect its trajectory. A deviation of a few thousand kilometers might be inconsequential for the primary nucleus, but it carries significant implications if the comet has shed fragments. These fragments can diverge. If R2 is fractured, if it has broken into multiple pieces, those constituent parts will possess slightly different velocities. Over time, they will disseminate along the orbital path, forming a trail of debris. Larger fragments exhibit less divergence. Smaller fragments, dust particles and pebbles can disperse widely. Consequently, if Earth traverses this debris stream, we will observe an escalation in meteor activity, perhaps a meteor shower of exceptional intensity, or potentially something more severe. The comet's current luminosity is estimated at magnitude 6.7 as of October 10th, 2025. This is dimmer than anticipated, though not unexpected. Comets diminish in brightness as they recede from the Sun. The critical inquiry is whether R2 will experience another outburst. If it does, if its brilliance suddenly increases, this will signify a resurgence of activity, possibly leading to fragmentation or a new expulsion of volatile materials, thereby altering the perceived risk level. Visual aids can enhance comprehension. Envision the Sun at the focal point. Earth's orbital path is depicted as a circular trajectory around it, with a radius of approximately 150 million kilometers. R2's orbit is an elongated ellipse, originating from the outer solar system, swinging past the Sun and then embarking on its outward journey. The two orbital paths intersect, but not concurrently. The comet passes through the intersection point in October. Earth arrives at this same point several months later. The disparity is both spatial and temporal. As long as both conditions persist, we are secure. However, comets are inherently unpredictable. They do not adhere to rigid timetables. They exhibit irregular movements, fracture, and shed debris, and these fragments do not precisely follow the parent object's path. They drift, they disperse, and occasionally they materialize when least expected. Our subsequent discussion will address the domain of observation, the public's fascination, the diversions that capture attention, and the influence of media reporting on our focus. Section 5 delves into the immediate observational landscape, viewing opportunities, media synergy, and public distraction. October promises a sky bustling with celestial activity. The comet R2 is approaching its closest proximity to Earth, reaching its peak visibility around October 20th. However, it is not the sole celestial visitor. Comet C2025A6, also identified as Lemon, is concurrently intensifying in brightness and becoming observable in the northern hemisphere around the same time frame. Two comets, both within the reach of amateur astronomers' instruments, both making their closest approaches within days of each other. This presents a remarkable spectacle. Such occurrences are infrequent. It is the kind of event that inspires people to gaze upward. Furthermore, there is the Orionid meteor shower. The Orionids typically reach their zenith annually around October 20th to 21st, coinciding with Earth's passage through the debris trail of Comet Halley. Indeed, Halley, the celebrated comet, renowned for its 76-year orbital period. Even when Halley is distant, its residual trail persists. This consists of a dispersion of ice and dust fragments following its orbital path. Each October, Earth intersects this stream, causing particles to impact our atmosphere at a velocity of 70 kilometers per second. They combust, generating luminous streaks, known as meteors. The Orionids typically yield between 10 and 20 meteors per hour at their peak, occasionally more. While not a major celestial storm, its regularity is dependable. Therefore, on the evening of October 20th, 2025, observers will witness two comets in the sky alongside a meteor shower at its maximum intensity. The heavens will be active, media coverage will be extensive, astronomy aficionados will inundate social media platforms with photographic evidence. News organizations will publish articles chronicling the celestial display. This offers an ideal moment for public engagement. It also presents a perfect opportunity for distraction. For while everyone's attention is directed towards the Orionids, while astrophotographers are diligently capturing images of the two comets, and while headlines extol the grandeur and marvel of the cosmos, very few individuals will be posing the more challenging questions. How precise is our knowledge of R2's trajectory? What is its margin of error? Has it undergone fragmentation? Are we monitoring its debris? What are the potential ramifications of an unforeseen event? The Washington Post reported on the dual comet phenomenon, noting that both R2 and Lemon would be visible to individuals equipped with binoculars or small telescopes. They underscored the rarity and beauty of the occasion, emphasizing the chance to observe two comets simultaneously. They did not highlight the proximity. They omitted any mention of the margin of error. They did not address the potential risk of fragmentation. This is not a critique, but rather a reflection of the nature of public science communication. Spectacle generates interest. Risk assessment does not. Additionally, there is 3 Atlas, the interstellar visitor, which continues to command significant media attention, despite its projected passage at 1.8 astronomical units, a distance considered safe by all standards. The media finds 3 Atlas captivating due to its enigmatic nature. It originated from another stellar system. Its coloration is reported as red or perhaps green, depending on the specific observation consulted. It appears to alter its color, an unusual characteristic. Asteroids typically do not exhibit such behavior. This has fueled speculation regarding artificial origins, extraterrestrial probes, and encoded messages within its trajectory. While improbable, these narratives are exciting and highly shareable. Meanwhile, R2, the more proximate visitor, possessing an imprecise orbit and a history of outbursts, receives less prominent coverage. It is less exotic. It is a native of our solar system, likely originating from the Oort cloud. There is nothing interstellar about it. It is perceived as merely another comet. However, this perception is inaccurate. It is a comet that remained undetected until it was remarkably close. It is a comet that concealed itself within the sun's glare, emerging only after passing perihelion. It is a comet that may have fragmented and could still fragment. It is a comet whose margin of error is 7 million kilometers, a disconcertingly small figure. Public perception is heavily influenced by novelty. 3 Atlas embodies novelty. R2 does not. Consequently, 3 Atlas garners the headlines, while R2 is relegated to a footnote. Yet, footnotes can harbour danger. Footnotes can obscure crucial information. It is essential to acknowledge behavioural caveats here. Comets are not dependable celestial bodies. Their brightening and dimming patterns are unpredictable. They fragment without prior indication. Predictions are educated estimations based on past behaviour. However, each comet is unique. R2 might intensify to magnitude 4, becoming visible to the naked eye. It might fade to magnitude 8 and vanish from view. It might disintegrate into fragments, creating a field of debris. Or it might exhibit no remarkable activity and quietly recede into the outer solar system, largely forgotten within a year. We lack certainty. What we do know is that this scenario does not constitute an impact alert. The current orbital solution indicates that R2 will pass Earth at a distance of 39 million kilometers. This is not close enough for a direct collision, but it is sufficiently proximate for other phenomena. It is close enough for interactions with debris. It is close enough for an increased flux of meteors. It is close enough that if the comet unexpectedly fragments, some of its constituent pieces could diverge onto trajectories that intersect Earth's path. This encapsulates the nature of cosmic risk. It is not a binary state of safety or peril. It is probabilistic, uncertain, and interwoven with numerous contingencies. Furthermore, our detection systems, the network of telescopes and surveys we rely upon for warnings, are not engineered to manage contingencies. They are designed to track predictable celestial objects on stable orbits. When unforeseen events occur, such as an object evading detection due to glare, a sudden brightening, or the shedding of fragments, both the system and we struggle to adapt. Our next segment will delve deeper, examining past near misses, asteroids that approached Earth with minimal warning, and detection failures that are more prevalent than commonly acknowledged. Section 6 presents case studies of asteroids discovered just before or after their close encounters with Earth. In early 2025, an asteroid designated 2025 TF passed within approximately 400 kilometers of Earth's surface. 400 kilometers, that is closer than the International Space Station. It is closer than most operational satellites. It lies within the orbital altitude of numerous space assets, and we remained unaware of its approach until it was nearly upon us. 2025 TF is small, likely only a few meters in diameter. At that size, even if it had entered the atmosphere, it would have disintegrated, producing a brilliant fireball, but causing no terrestrial damage. The Chelyabinsk meteor event in 2013 involved an object approximately 17 to 20 meters in diameter, which detonated in the air with a force equivalent to several hundred kilotons of TNT. This event shattered windows and injured over 1,500 individuals, yet did not result in a crater. 2025 TF was smaller. Its passage would have been a visual spectacle, nothing more. However, the crucial point here is not its size, but the detection latency. We did not detect it until it was virtually overhead. It traversed the skies over Antarctica, one of Earth's most remote regions, where very few observers were present. Had its arrival occurred a few hours earlier or later, or had its trajectory been slightly altered, it might have passed over a populated area, leaving us entirely without warning. This is not an isolated occurrence. In recent years, several small asteroids have been identified only days, hours, or even minutes prior to their closest approach. Some were detected only after they had already passed. They traversed Earth's vicinity, undetected by our surveys, and we only identified them on their outward journey. This phenomenon arises from the inherent limitations of our detection network. Telescopes possess minimum thresholds for detecting brightness. Small objects are inherently faint. If they approach from the direction of the sun, they are obscured. If they travel at high velocities, they cross the sky too rapidly for automated survey systems to acquire them. If they possess low albedo, meaning they reflect very little sunlight, they blend seamlessly into the background. Detection bias is not merely a theoretical concern. It represents a practical, observable mode of failure. We miss objects. We frequently miss them, and typically, we only become aware of these missed detections when an individual happens to observe a specific area of the sky at the opportune moment and notices a moving anomaly. The ramifications of these near misses are more substantial than one might initially assume. While most small asteroids disintegrate harmlessly in the atmosphere, not all do. Even a relatively small object, if it strikes a critical target, can inflict catastrophic damage. A few meters of rock impacting a satellite at orbital velocity would result in its immediate destruction. A collision with the International Space Station would be fatal. An impact on a city, even from a modest impactor, could raze structures and claim thousands of lives. The atmosphere serves as a shield, but it is not an infallible one. Objects exceeding approximately 20 meters in diameter can survive atmospheric entry and reach the surface. Even objects smaller than this can produce destructive airbursts. Furthermore, there is the issue of debris. When an asteroid disintegrates within the atmosphere, it disperses fragments over a wide area. While most fragments are small, some can be substantial enough to cause damage. If the fragmentation event occurs over a densely populated region, these fragments become projectiles. The Chelyabinsk event scattered meteorites across hundreds of square kilometers. Individuals collected these fragments as mementos. However, had the object been larger, or had the fragmentation occurred at a lower altitude, the resulting fragments would have posed a more significant threat. Now, let us scale this scenario. Instead of a single, small asteroid, imagine a cloud of debris emanating from a fragmenting comet. Instead of a few meters of rock, envision hundreds or thousands of pieces, ranging from fine dust to sizable boulders, dispersed along the comet's orbital path. Instead of a singular point of impact, consider a diffuse threat, a statistical hazard where the likelihood of any individual piece striking a specific target is low. However, the aggregate probability, the cumulative chance of an impact, is not negligible. This is what transpires when comets fragment. They do not deliver a single projectile, rather they unleash a barrage. R2 possesses an aphelion distance of 7 million kilometers. This represents the separation between Earth's orbit and the comet's orbit. If the comet fragments, and if its pieces disperse along the orbital path, some of these fragments might drift closer to Earth's trajectory. Not to zero distance, not to the point of impact, but closer. Close enough that the statistical probability shifts from negligible to a small but non-zero value. And a small but non-zero probability is sufficient to cause unease among risk analysts. This is the fundamental lesson derived from 2025 TF and similar events. Detection latency is a tangible reality. We do not detect everything. We miss the majority of objects if they are small, fast-moving, or approaching from an unfavourable direction. The asteroids we successfully track are those that adhere to predictable patterns, those that arrive on expected trajectories from known directions at anticipated times. Those that deviate from these predictable behaviours are the ones that instill apprehension, because they are the ones we fail to detect. In our next segment, we will examine how comets can pose hazards even without direct impact, exploring how their debris and dust trails create persistent dangers long after the parent object has moved on. Section 7 addresses comet fragmentation and the hazard presented by dust trails, exploring realistic speculative scenarios. Even if a comet misses Earth, its fragments can inflict damage. Allow me to elucidate this phenomenon. Comets are not monolithic celestial bodies composed of solid rock. They are loosely aggregated collections of ice, dust, rock, and organic compounds, held together by weak gravitational forces and surface tension. Consequently, they are inherently fragile. As they approach the Sun, thermal stresses induce fracturing. Outgassing generates internal pressure, leading to their separation. Tidal forces, particularly when a comet ventures too close to a massive celestial body, can tear them apart. Sometimes fragmentation occurs subtly, releasing small pieces. At other times, it is a dramatic event, with the comet shattering into dozens of fragments. Comet Shoemaker-Levy 9 serves as a prominent example. In 1992, it passed too close to Jupiter and was subsequently fractured by tidal forces. The resulting fragments, numbering more than 20, dispersed along its orbital path. 2 years later, these fragments impacted Jupiter sequentially, triggering colossal explosions observable from Earth. Each impact released energy comparable to millions of nuclear detonations. The atmospheric disturbances on Jupiter persisted for months. While spectacular, this event also demonstrated the fragility of comets and the potential danger posed by their fragments. Another illustration is Comet 73P Schwarzmann-Wachmann. This comet has undergone multiple fragmentation events. In 1995, it divided into several pieces. In 2006, it fragmented again, this time into numerous smaller chunks. Observers witnessed in real time the comet's disintegration, with each fragment developing its own coma and tail. The fragments continued their dispersal, each following a slightly divergent trajectory. Over time, they coalesced into a debris stream, akin to a river of ice and dust flowing along the original orbital path. Earth has passed through portions of this stream, resulting in a transient increase in meteor activity. While not catastrophic, it was observable. Now let us apply this understanding to R2. The comet has already experienced at least one outburst, indicative of internal instability. If it fragments, the resultant pieces will diverge. The rate of divergence is contingent upon the relative velocities of the fragments, which in turn depend on the energy of the fragmentation event. A gentle separation results in slow dispersal. A violent explosion leads to rapid separation. Regardless of the mechanism, over time the fragments spread out, as does the dust they generate. Dust constitutes the primary hazard. Every comet continuously sheds dust through sublimation. These dust particles are minuscule, ranging from microns to millimeters in size, yet they travel at speeds of tens of kilometers per second. At such velocities, even a grain of sand possesses considerable kinetic energy. If a dust particle impacts a spacecraft, it can puncture the hull. If it strikes a satellite, it can damage solar panels, sensors, or communication systems. If it impacts a human undertaking a spacewalk, it could prove fatal. The International Space Station, for instance, is equipped with shielding designed to protect against micrometeoroids. These shields are multi-layered, engineered to vaporize incoming particles before they can penetrate the hull. However, these shields are not impervious. Larger particles, or those arriving at unconventional angles, can bypass them. The ISS has sustained multiple impacts. While most strikes cause minor damage, some have necessitated repairs. A dense meteoroid stream, such as one generated by a fragmenting comet, significantly elevates the risk. Now, consider the geometrical aspect. R2's aphelion distance is 7 million kilometers. This is the minimum separation between the comet's orbital path and Earth's orbital path. If the comet fragments and its fragments disperse along the orbit, some of them could drift closer to Earth's path. Not to the point of intersection, but closer. And if Earth passes through the debris stream at an inopportune moment, we might encounter a higher than average flux of particles. This could manifest as an amplified meteor shower. It could result in damage to satellites. It could lead to micrometeoroid impacts on spacecraft. The probability of any single particle striking a specific target is low. Space is vast, and targets are relatively small. However, the aggregate probability, the overall chance of an object being struck, is higher. We currently have a substantial number of objects in orbit, thousands of satellites, space stations, and various spacecraft. All of these are potential targets. Furthermore, there is the scenario involving atmospheric interaction. If Earth traverses a dense dust stream, even if the particles are small, the cumulative effect might be observable. High-altitude atmospheric glow could increase. Bolide activity, bright meteors that explode in the upper atmosphere, might spike. Amateur astronomers would notice. Meteor monitoring cameras would record an anomaly. This would not be catastrophic, but it would be unusual, and unusual events tend to trigger alerts. The primary concern is not the dust that is visible, it is the fragments that remain undetected. A boulder-sized chunk, perhaps 1 or 2 meters in diameter, travelling at 30 kilometers per second, would be virtually invisible until it was too late. Optical survey instruments might detect it, but only if they were coincidentally observing the correct region of the sky at the precise moment. If the fragment approached from the direction of the sun, it would be undetectable. If it possessed a low albedo, indicating a dark surface, it would be nearly impossible to spot. And if it impacted the atmosphere over a populated area, the outcome would be comparable to the Chelyabinsk event, or potentially worse. Estimating the probability in this context is challenging. We do not know if R2 is fragmented. We do not know if it will fragment. We do not know the potential number of fragments or how they might disperse. We lack information regarding the size distribution, velocity distribution, or trajectory distribution of these hypothetical fragments. All we possess is the orbit of the parent comet and a 7 million kilometre gap between that orbit and Earth's path. Within these parameters, we can assert that the probability of a fragment impacting Earth is low. However, low is not synonymous with zero, and when the consequences of an incorrect assessment are measured in terms of human lives and infrastructure, a low probability may not be sufficiently reassuring. Visualization can be beneficial here. Once again, envision the comet's orbital path as a thread suspended in space. Now, imagine that thread fraying, splitting into dozens or hundreds of finer threads, each deviating slightly from the original. Some threads remain close to the parent path, while others drift away. This cluster of threads expands over time, forming a diffuse ribbon along the orbital trajectory. Earth's orbit is another thread, intersecting this ribbon at an angle. For the majority of the time, Earth passes through empty space, but on occasion it traverses the ribbon, and when this occurs, the particles within the ribbon rain down. This is not mere speculation, it is a phenomenon with a historical precedent. Meteor showers are precisely this occurrence. The Perseids, the Leonids, the Orionids, all are derived from debris streams originating from comets. Annually, Earth intersects these streams, resulting in visible meteors. Typically, this is a benign event. Occasionally, it is spectacular. Very rarely it poses a danger. In 1833, the Leonid meteor storm generated tens of thousands of meteors per hour. Witnesses described the sky as ablaze. If such an event were to occur today, with our extensive satellite infrastructure, the resulting damage would be severe. R2 is not predicted to generate a meteor storm. Its debris, if it exists, is likely too sparse. However, we cannot be certain. We will not know until we observe it directly, and by the time we can observe it, it may be too late to take any action other than to witness the event unfold. In our next segment, we will pose a more encompassing question. Are we witnessing an increase in unexpected celestial visitors, or is this simply a reflection of observational bias? Is the solar system actually sending us more objects, or are we only now beginning to detect them? Section 8 focuses on pattern recognition and the question of whether we are observing a surge of surprise visitors. Allow me to enumerate them for you. Oumuamua arrived in October 2017, marking the first confirmed interstellar object detected passing through our solar system. It was anomalous, elongated, exhibiting tumbling motion and accelerating in ways inconsistent with outgassing models. It vanished before we could properly analyze it. Then, in August of 2019, came Borisov, our second visitor from beyond the solar system. This one was unmistakably a comet, complete with a coma, a tail, and a composition that aligned perfectly with what we anticipate from stellar remnants. Now, we have 3 Atlas, detected in 2025, another extraterrestrial entity. This particular object is considered an asteroid or perhaps a comet nucleus, depending on one's perspective. Its colour shifts, it's quite peculiar. And while the world's attention is fixed on the 3 Atlas, R2 quietly slips in from our own solar system's vicinity, going entirely unnoticed until after it passed its closest point to the Sun. That's 4 such objects in just 8 years: Oumuamua, Borisov, 3I Atlas, and R2. They hail from different origins, possess distinct compositions, and were discovered under varying circumstances, yet each one was entirely unexpected. All of them arrived with little to no prior warning. Is this a trend? Is this an increase in frequency? Or is this simply the consequence of us finally intensifying our observation efforts? There are 3 prevailing hypotheses. The first is observational bias. We now possess superior instruments, more sophisticated telescopes, expanded sky coverage, more comprehensive surveys, and a greater number of amateur astronomers equipped with access to professional-grade data. We're actively searching with greater diligence, and consequently, we're discovering more. Survey systems such as Pan-STARRS and the forthcoming Vera C. Rubin Observatory are specifically engineered to detect transient phenomena, moving celestial bodies, and any event that exhibits change. As these systems become operational and their capabilities advance, the rate of detection naturally increases. This does not imply an escalation in the number of objects arriving. Rather, it signifies that we are finally discerning the celestial bodies that have always been present. The second hypothesis posits a genuine increase in the dynamical flux. It's possible that something is perturbing the Oort cloud. Perhaps a passing star, long departed, sent a ripple of comets inward, and we are only now witnessing the initial arrivals. It could also be that our solar system is traversing a region of space characterized by a higher density of debris. Galactic tides, the gravitational influence exerted by the Milky Way structure, might be nudging more comets toward the inner system. This scenario is not beyond the realm of possibility. The Oort cloud is vast, containing trillions of comets. Even a minor perturbation could direct thousands of them inward over the span of several thousand years. From our perspective, constrained by the brevity of human lifespans, this would appear as a sudden surge. The third hypothesis centers on statistical clustering. It suggests pure coincidence. Random processes inherently generate clusters. If you flip a coin 100 times, you're likely to observe runs of heads or tails. This does not indicate that the coin is biased. It merely demonstrates that randomness tends to clump. 4 unexpected visitors within an 8-year period could simply represent statistical noise, a fluctuation without any deeper significance. In another 8 years, we might detect none, or we might identify 10. Without additional data, differentiating between a genuine signal and mere noise remains impossible. Each of these hypotheses is supported by evidence. The notion of observational bias is compelling. The count of known near-Earth asteroids has surged dramatically over the past 2 decades, not due to a sudden proliferation of asteroids, but rather because we initiated a systematic search for them. The same likely holds true for comets. The Zwicky Transient Facility has identified thousands of comets, the majority of which are sun grazers, simply because it can detect objects that optical telescopes cannot. As our detection network expands, so does our catalogue. However, observational bias does not account for every anomaly. Oumuamua was undeniably peculiar. Its elongated form, its non-gravitational acceleration, and its complete absence of a visible coma defied straightforward explanations. Some astronomers theorized it was a fragment of a planet that had been shattered by tidal forces within another star system. Others proposed it was an iceberg of hydrogen, a nitrogen iceberg, or a sliver of frozen gas. The hypotheses became progressively more unconventional because the simpler explanations failed to align with the observations, and then it departed, leaving us with the missed opportunity to study it further. 3i Atlas also presents an enigma. Its colour appeared to shift from red to green, depending on the reliability attributed to specific observations. Asteroids do not typically exhibit such behaviour. Colour is indicative of surface composition. A change in colour suggests a modification in composition, implying that the surface is not uniform. Perhaps it rotates, with different sides reflecting distinct wavelengths. It's possible it's subtly outgassing, and the resultant coma is influencing the observed spectrum. Or it could be something else entirely. We lack definitive answers because we have not approached it closely enough for detailed examination. R2 conforms to the pattern in a distinct manner. It is not an interstellar object. It is native to our solar system, likely originating from the Oort cloud. However, it concealed itself within the sun's glare and only emerged after its perihelion passage, thereby illustrating how easily we can overlook objects, even within our immediate cosmic neighbourhood. If R2 can remain hidden, then so too can others. How many long-period comets traverse the inner solar system undetected each year? We do not have an answer. We only observe those that become sufficiently bright, remain visible for an adequate duration, and cross our detection thresholds. The remainder are effectively spectral apparitions. Is there a discernible pattern? Possibly. The optimistic interpretation is that our capacity to perceive the universe as it truly is, a dynamic expanse teeming with transient visitors, debris flows, and unforeseen arrivals, is improving. The pessimistic interpretation suggests that the frequency of these arrivals is escalating, and we are unprepared. The realistic interpretation likely resides somewhere between these extremes. We are detecting more because our observational efforts are more intensive. However, we're also discovering that the baseline rate of cosmic transit is higher than we had previously estimated. Our solar system is not a tranquil locale. It is a cosmic thoroughfare, and we are only now deploying traffic monitoring systems. Next, we will examine the institutions responsible for managing this traffic, the data processing workflows, the points of congestion, and the silences that sow suspicion. Part N: Institutions, Silence, and the Information Lifecycle. Allow me to guide you through the process by which a discovery transitions into public awareness. An observer, whether a professional astronomer or an amateur enthusiast, identifies something unusual, a moving object, a source of increasing brightness, or a transient event. They meticulously record its position, the precise time of observation, and its apparent magnitude. Subsequently, they ascertain whether this object has already been catalogued. If it has not, they submit a report. To where do they report it? To the Minor Planet Center, or MPC, an entity managed by the International Astronomical Union. The MPC serves as the central clearinghouse for observations pertaining to asteroids, comets, and other small celestial bodies. It aggregates data from observers worldwide, verifies its accuracy, and issues circulars upon the confirmation of novel discoveries. However, the verification process inherently requires time. A solitary observation is insufficient. Multiple observations are necessary to confirm the object's actual existence, to eliminate the possibility of instrumental artifacts, and to calculate a preliminary orbit. This necessitates waiting for other observers to direct their telescopes toward the same sector of the sky and corroborate the initial sighting. If the object is faint, if it resides near the detection limit, or if it is moving at high velocity, confirmation may take days, or occasionally longer. Once confirmed, the MPC assigns a provisional designation and disseminates an electronic circular. The data is publicly accessible to all, but it consists of raw observations, orbital elements, position vectors, and magnitude estimations. It is not a press release, nor is it a headline. It is a technical document intended for the astronomical community. The general public does not typically peruse MPC circulars. They consume news articles, and these news articles, if they appear at all, emerge at a later stage. In the interim, other institutions refine the orbital data. The Jet Propulsion Laboratory, or JPL, operates the Horizon System, a sophisticated tool for calculating precise trajectories of solar system objects. As more observations become available, the orbital solution improves, uncertainties diminish, and predictive accuracy becomes more reliable. If the object is deemed potentially hazardous, meaning its orbit brings it into close proximity with Earth, JPL will flag it. The Center for Near-Earth Object Studies, or CNEOS, then assesses the associated risk. If the risk level is deemed sufficiently high, NASA will issue a formal statement. Conversely, if the risk is low, they may refrain from doing so. For R2, the procedure unfolded as follows. Vladimir Bazugi, an amateur astronomer, detected the object within ZTF data on September 11, 2025. He promptly reported his finding. Subsequent observations by other astronomers optically confirmed its presence. The MPC then issued a circular, assigning it the designation C2075R2. JPL proceeded to calculate its orbit, and CNEOS evaluated the risk. The conclusion was that it posed no threat. Its closest approach was projected to be 0.26 astronomical units, a distance sufficiently great to ensure safety. Consequently, there was no press release and no public warning, merely a technical update embedded within a database. And this is precisely where the silence originates, not because of any intentional concealment or a conspiracy, but rather because the system is architected for risk mitigation, not public engagement. If an object does not represent a threat, it does not generate headlines. And when an object fails to attract headlines, the vast majority of people remain unaware of its existence. R2 received mention in a handful of astronomical publications and a few space news websites. It was featured as the astronomy picture of the day on September 18th. However, it did not trend on social media and did not dominate the news cycle. It was simply another comet, one of dozens discovered annually. Contrast this with the interstellar object 3I Atlas, with its mysterious colour-changing properties and peculiar acceleration. That is headline material. That is the kind of narrative that captures the attention of mainstream media, proliferates across social platforms, and sparks discussions in comment sections. The fact that 3I Atlas poses no danger, that its closest approach will be 1.8 astronomical units, and that it presents no threat is irrelevant. What matters is its inherent interest factor and interest cells. This situation fosters a vacuum when institutions fail to provide detailed and accessible updates, when the information dissemination process is protracted and technical, and when the interval between discovery and public awareness stretches to weeks or even months. Speculation inevitably fills the void. Social media users take note of these informational gaps. They pose questions. Why are we not hearing more about this? Why is the media coverage so sparse? Is something being concealed? And in the absence of official pronouncements, unofficial explanations begin to surface. Theories, conspiracies, and rumours. Vladimir Bazugi's discovery of R2 is particularly instructive in this regard. He is not a professional astronomer. He does not work for a space agency. He is an amateur who possesses the skills to analyse ZTF data. The fact that he identified the comet before the professional surveys did is not indicative of a failure on the part of the professionals. Rather, it serves as a potent reminder that our detection network has vulnerabilities, that non-traditional avenues of discovery are significant, and that sometimes the most crucial observations originate from unexpected sources. However, it also provokes further questions. If an amateur can locate a comet that eluded professional surveys, what else might we be missing? How many objects traverse the inner solar system undetected simply because they happen to be in the wrong place at the wrong time? Perhaps the surveys are focused elsewhere, or the sky is too light polluted, or the weather is unfavourable, or the instrument is undergoing maintenance. We do not know. We cannot know. And that is the crux of the problem. The information life cycle is intentionally slow. Verification protocols are in place to prevent false positives. Cautionary measures are implemented to avert public panic. However, this caution also creates informational gaps, and these gaps breed doubt. When individuals lose faith in institutions to provide truthful accounts, they seek alternative sources of information, and these alternative sources are not always reliable. Next, we will undertake a triage of unconventional ideas, conspiracy theories, and fringe notions. We will endeavour to distinguish between those claims that warrant consideration and those that do not. Part 10. Wildcards and Conspiracies. Let me be unequivocally clear. Certain individuals will assert that R2 is not a naturally occurring object. They will contend that it is a probe, a craft, an engineered device dispatched by an entity, or entities, to observe us. They will argue that its trajectory is suspiciously convenient, its timing too perfect, and its outburst too deliberately controlled. They will claim that NASA possesses more information than it is revealing, that the imagery is being suppressed, and that the authentic data is classified. They will propose that this represents a message, a warning, or a test, and they will genuinely believe these assertions. Therefore, let us subject these claims to a rigorous assessment. Let us examine each one individually and determine which merit any degree of attention. Claim 1. R2 is an artificial object. Is this physically plausible? In principle, yes. Any civilization sufficiently advanced could construct a spacecraft designed to emulate the appearance of a comet. They could coat it with ice to generate a coma upon heating. They could program it to produce outbursts at specific intervals. They could engineer its trajectory to pass in close proximity to Earth. It is indeed possible, but it is not a simple undertaking, and it inevitably leaves discernible traces. If R2 were artificial, we would anticipate anomalies. Spectroscopic analysis would reveal unusual compositions, elements, or molecules that deviate from the expected chemistry of natural comets. The nucleus would exhibit structures, geometric patterns, and regularities absent in natural celestial bodies. The trajectory would demonstrate precise control, with minute adjustments inconsistent with natural outgassing. Furthermore, there would likely be electromagnetic emissions, such as radio signals or infrared signatures, indicating the presence of active systems. We have observed none of these indicators. Its spectrum closely resembles that of a typical comet. Its coma is consistent with the sublimation of ice. Its trajectory adheres to gravitational dynamics. There are no discernible signals of artificial origin. Occam's razor dictates that the simplest explanation is generally the most accurate. R2 appears to be a comet because it is in fact a comet. Invoking an artificial origin necessitates introducing extraneous assumptions, increasing complexity, and positing the existence of actors with unknown motives and capabilities. While possible, it is not essential. In scientific reasoning, we refrain from proposing explanations that are not strictly necessary. Claim 2. The images are being suppressed. Are we seeing everything? Almost certainly not. Professional observatories do not release every single image they capture. They process data, perform calibrations, filter out noise, and select the most compelling frames. Some data is considered proprietary, reserved for the research teams that initiated the observations. Some data is of insufficient quality to warrant public release. However, suppression implies deliberate intent, a coordinated effort to withhold information, and this would require a level of coordination that is exceedingly difficult to achieve. Observatories are dispersed globally and operate independently. Amateur astronomers possess their own observational equipment. If a truly dramatic phenomenon were visible, someone would undoubtedly post it. The absence of dramatic imagery suggests that no such imagery exists, rather than implying that it is being actively concealed. Claim 3. The trajectory is being manipulated. Could an external force be guiding R2? If by external force you refer to extraterrestrial intelligence, then we revert to Claim 1. If, however, you are referring to natural forces, then the answer is yes. Outgassing generates non-gravitational accelerations. Comets are not purely ballistic. They exert forces upon themselves by expelling gas. R2 has exhibited outbursts, indicating it is venting gases that influence its trajectory. JPL's orbital models incorporate non-gravitational forces, accounting for the effects of outgassing. While the trajectory predictions are not flawlessly precise, they are remarkably accurate. If the comet were under active, deliberate control, we would observe deviations from the models that could not be attributed to outgassing. We have not detected any such deviations. Claim 4. This is harmless, but symbolic. Some individuals argue that even if R2 poses no threat and will not impact Earth, its arrival carries profound significance, serving as a sign, an omen, or a synchronistic event. This is not a scientific claim. It is a philosophical or spiritual assertion. Science can precisely determine an object's orbit, its composition, and its probability of impact. It cannot ascertain whether the universe is conveying a message, as this falls outside the purview of empirical inquiry. If you derive personal meaning from the arrival of a comet, that is entirely your prerogative. However, it is crucial not to conflate personal significance with physical risk. Now, are there any claims that warrant more careful examination? Yes. 1. The potential for fragmentation and the associated debris hazards are a genuine concern. This is not a conspiracy theory, it is a matter of physics. If R2 were to fragment or shed pieces that deviate from its primary trajectory, those fragments could indeed present a hazard. While an impact hazard is unlikely, a debris hazard, such as an increased flux of micrometeoroids or a threat to satellites, is a plausible scenario that warrants monitoring and preparedness. This is speculative, but it is grounded in our established understanding of cometary behavior. The triage matrix can be summarized as follows. Artificial origin is not feasible without supporting evidence. Image suppression is improbable given the distributed nature of astronomical observation. Trajectory manipulation is unsupported by evidence beyond natural outgassing. Symbolic meaning lies outside the scientific domain. Fragmentation and debris hazards are plausible and merit ongoing tracking. Speculation can be enjoyable. It is an inherent aspect of human nature to perceive patterns, imagine agency, and fill informational voids with narratives. However, we must always remain prepared to rigorously test these narratives against empirical data, and when the data fails to substantiate a particular narrative, we must possess the discipline to abandon that narrative and proceed. Next, we will transition to a different topic. We will explore other recent scientific headlines, commencing with neuroscience, as the brain itself functions as a detection system, albeit one with its own inherent blind spots. Part 11. Neuroscience. UCSF discovers protein that slows brain aging. In August of 2025, researchers at the University of California, San Francisco, published findings concerning a protein that appears to regulate the aging process of the brain. This protein, identified through experiments conducted on aged mice, seems to function as a brake on neural plasticity. When the researchers inhibited this protein, the aged mice exhibited improvements in memory and learning. Their neurons fired with increased reliability, and their synaptic connections strengthened. By several measures, their brains began to function akin to those of younger specimens. The experimental procedure was straightforward. Take aged mice, identify the protein that accumulates with advancing age, block its activity through pharmacological or genetic intervention, and then assess whether behavioral improvements occurred. The results were promising. Aged mice that underwent the treatment demonstrated enhanced performance on memory-related tasks. They navigated mazes more rapidly and recognized objects with greater accuracy. The observed effects were measurable, reproducible, and statistically significant. However, this research was conducted on mice. Mice are not humans. Their brains are simpler, smaller, and organized differently. What proves effective in a mouse does not always translate to human application. The history of neuroscience is replete with treatments that have successfully cured mice, but subsequently failed in human clinical trials. Alzheimer's disease, for instance, has been effectively treated in mice on dozens of occasions, yet humans continue to await a cure. Therefore, caution is essential. While the findings are encouraging, they are preliminary. The potential implications, if they are indeed applicable to humans, are profound. Cognitive decline is one of the most widely feared aspects of aging. Memory loss, difficulties with learning, and slowed processing capabilities can diminish independence and erode a person's sense of self. If the inhibition of a single protein could mitigate or even reverse this decline, the impact would be transformative, not only for individuals but also for societies grappling with aging populations. The global economic cost associated with dementia is measured in trillions of dollars. A treatment that could delay its onset by even a few years would conserve immense resources and alleviate considerable suffering. However, challenges remain. Proteins do not operate in isolation. They are integral components of complex networks, cascades, and feedback loops. Inhibiting one protein could trigger downstream effects, potentially disrupting other physiological systems. The aged mice in the study did not exhibit overt side effects, but their observation period was relatively brief. Long-term consequences remain unknown, and humans are inherently more complex organisms. We live longer lives, accumulate greater cumulative damage, and possess a higher incidence of coexisting medical conditions. A treatment that functions seamlessly in a mouse might interact in unpredictable ways with human physiology. Consider this analogy. The brain serves as a detection system. It constantly scans its surroundings, processes incoming signals, forms memories, and generates predictions. When functioning optimally, it captures intricate details and demonstrates adaptability and learning. As it ages, its sensitivity diminishes. Signals weaken, noise encroaches, and discerning patterns becomes increasingly difficult. The protein identified by the UCSF researchers appears to be implicated in this process of degradation. By inhibiting its activity, the researchers were able to restore some of the brain's youthful responsiveness. Now, reflect upon our astronomical detection systems. Telescopes scan the celestial sphere, process incoming signals, catalogue celestial objects, and predict their trajectories. When operating effectively, they detect faint comets, track asteroids, and provide warnings of potential hazards. However, these systems are also susceptible to degradation. Instruments age, sensors drift, calibration accuracy wanes, data pipelines become contaminated with noise, and over time, we begin to miss phenomena that were previously within our observational grasp. While the parallel is not perfect, it offers valuable insight. Both systems, biological brains and technological telescopes, are designed to identify patterns within environments characterized by noise. Both are subject to deterioration over time. Both can, at least partially, be restored through targeted intervention. For brains, this intervention might involve a protein inhibitor. For telescopes, it could entail recalibration, sensor replacement, or the implementation of upgraded algorithms. The underlying principle remains consistent. Maintaining vigilance necessitates ongoing maintenance. The UCSF investigation serves as a vital reminder that unseen processes govern our perception, dictating what we notice and what eludes us. These processes can be biological, such as age-related protein accumulation. They can be technological, like a sensor drifting out of calibration. Or they can be institutional, exemplified by a survey timetable that leaves critical periods unexamined. The remedy remains constant. Pinpoint the mechanism, comprehend its workings, and then implement an intervention to restore normal function. Moving forward, we will examine another headline from the realm of neuroscience. This particular article focuses on Alzheimer's disease, presenting an opportunity to dissect the recurring pattern of sensational claims juxtaposed with understated realities, a phenomenon worth understanding. This is part 12, the Alzheimer's reversal headline. October of 2025 saw an influx of sensational headlines proclaiming the reversal of Alzheimer's in mice. The accompanying articles were written with breathless excitement, and social media buzzed with hopeful pronouncements. In reality, the situation was far more complex. Researchers had investigated a novel intervention, potentially involving vascular restoration, amyloid clearance, or protein regulation. While the specific details varied across different studies, the overarching narrative was consistent. Aged mice exhibiting cognitive impairments demonstrated significant improvement following treatment. Their brains showed reduced plaque buildup, enhanced memory recall, and in some observed metrics, a reversal of the disease's pathology. This is not an unprecedented development. Over the past 2 decades, Alzheimer's research has yielded numerous promising findings from studies involving mice. These have included vaccines designed to clear amyloid, drugs aimed at reducing tau tangles, and gene therapies intended to restore synaptic function. These interventions have proven effective in mice, However, their translation to human treatments has largely resulted in failure, presenting an enormous gap in efficacy. Mouse models of Alzheimer's disease do not perfectly mirror the human condition. Mice have shorter lifespans, preventing them from developing the full spectrum of human pathology. Their brains are structurally simpler, their immune systems differ, and their metabolic rates are accelerated. Consequently, a treatment that demonstrates success in a 6-month mouse study may prove ineffective in a 10-year human trial. Sample sizes are also a crucial factor. Mouse studies often involve only dozens of animals, whereas human trials necessitate thousands of participants. The duration of these studies is another disparity. Mouse studies typically span months, while human trials extend for years. Potential side effects also differ dramatically. A drug that proves safe in mice might exhibit toxic properties in humans. Furthermore, efficacy can vary significantly. A treatment that boosts memory by 20% in mice might only achieve a 5% improvement in humans, a margin that may not be clinically significant. The Newsweek summary, characteristic of many popular science articles, focused heavily on the positive aspects: reversal, breakthrough, and hope, words that invariably attract readership. In contrast, the primary sources, the actual research papers, adopted a more measured tone, employing terms like preliminary, limited, and requires further study. These publications acknowledged the inherent challenges in translating findings from animal models to humans and refrained from declaring victory, opting instead to report progress. The core issue lies in how complex scientific findings are distilled into sensational headlines, leading to the erosion of nuance and the erasure of uncertainty. This widening chasm between the researchers' actual discoveries and the public's understanding fosters disappointment. When treatments eventually falter in human trials and clinical results prove negative, the public feels betrayed, having been promised a cure and instead receiving another setback. This erosion of trust is not confined to Alzheimer's research. It is a pattern observed across all fields where high stakes and intricate science converge, including cancer research, climate science, infectious disease studies, and indeed, astronomy. When a new comet is discovered, headlines often trumpet spectacular celestial displays, once-in-a-lifetime events, and naked-eye visibility. The reality, however, is frequently dimmer, more uncertain, and subject to unpredictable variables. Comets can fade, fragment, or simply fail to meet expectations. As a result, the public, anticipating a grand spectacle, often feels let down. The appropriate response to such situations is not cynicism, but skepticism. When confronted with a headline announcing a breakthrough, it is advisable to consult the primary source material. Examine the sample size, look for any qualifying statements, and inquire about what was actually measured versus what was inferred. Investigate the limitations and the planned next steps. More often than not, the answer will involve the need for further research, which is a perfectly valid outcome. This is the nature of scientific inquiry, though it contrasts sharply with the demands of headline writing. Headlines necessitate certainty, whereas science operates on probabilities. This situation bears a striking parallel to R2. The comet itself is real, the observations are factual, and the calculations of its orbit are accurate. However, predictions regarding its brightness, potential fragmentation scenarios, and visibility are all probabilistic. We cannot definitively state what will occur. We can only outline what might happen with varying degrees of likelihood. The responsible approach is to communicate these probabilities with clarity, avoiding both inflation and deflation, and steering clear of clickbait sensationalism. Next, we transition to the domain of artificial intelligence, another area where hype and reality often diverge. However, AI also represents a domain where genuine advancements are actively reshaping our ability to detect cosmic threats. This is Part 13, AI, October 2025, Model and Tool Releases and Ethical Considerations. October of 2025 witnessed the unveiling of numerous artificial intelligence announcements, including new models, tools, and expanded capabilities. Open source releases push the boundaries of machine learning, introducing foundation models with enhanced reasoning abilities, improved context handling, and faster inference speeds. Companies and research laboratories presented systems capable of processing extended contexts, maintaining coherence across intricate reasoning sequences, generating code with greater reliability, and interacting with multiple sensory inputs simultaneously. The pace of development is exceptionally rapid. Tasks considered impossible just 2 years prior are now commonplace, and what is routine today will likely be obsolete within 2 years. This acceleration is tangible, measurable, and shows no signs of abating. Concurrently with this technical progress, ethical initiatives aimed at aligning AI development with human values gained momentum at global forums, supported by researchers and policymakers. While the specifics may differ, the underlying message is consistent. AI is a potent force, its development is accelerating, and it is imperative to ensure its alignment with our true desires, not merely what we believe we want, but what we genuinely value when faced with real consequences. The critical question is not solely what AI can accomplish, but what it ought to do, and who holds the authority to make that determination. These are not abstract philosophical debates. They are pressing practical concerns. As AI systems become more sophisticated, autonomous, and integrated into critical infrastructure, the stakes escalate. Errors in medical diagnostics can be fatal. Mistakes in traffic control can lead to accidents, and failures in astronomical detection could leave us vulnerable to impending threats. In astronomy, AI is already an integral part of data processing pipelines. This is not a hypothetical scenario but current practice. Automated anomaly detection systems meticulously scan survey images for transient events. Machine learning algorithms classify celestial objects, differentiating asteroids from stars, comets from galaxies, and supernovae from variable stars. These classifications occur within milliseconds, a task that would require humans minutes or hours to complete. Algorithms also refine orbital calculations, processing sets of positional measurements to determine trajectories. They predict future positions, estimate uncertainties, and flag objects whose orbits bring them into proximity with Earth. These systems identify potential hazards, objects that may pose collision risks, warrant follow-up observations, or require inclusion on watch lists. The sheer volume of data generated is beyond manual human processing capabilities. Modern wide-field surveys produce terabytes of data each night, with each image containing millions of sources. Every source must be measured, catalogued, and cross-referenced with existing databases. Transient phenomena, events involving the appearance, disappearance, or changes in brightness, must be identified and flagged. The Vera C. Rubin Observatory, upon its full operational status, will image the entire visible sky every few nights, detecting billions of objects. Tens of thousands of these will be in motion, undergoing changes, or exhibiting transient behavior. No human team could possibly process such a massive quantity of data. AI is essential for sifting through this information deluge to uncover signals buried within the noise. Without AI, contemporary astronomy would be overwhelmed by its own success, drowning in the sheer volume of information streaming from telescopes nightly. However, AI is not infallible. It is prone to errors. It can generate false positives, identifying objects that appear to be hazards but are not. A cosmic ray striking a detector can create a bright streak, which the AI might interpret as a fast-moving object and flag as a potential asteroid. Subsequent observations would reveal nothing, indicating the object was an artifact, a glitch, or a phantom. Alternatively, the AI might misclassify objects. A distant supernova that brightens gradually might exhibit a light curve resembling that of a variable star. The AI could assign it to the incorrect category, delaying its proper identification for days, by which time the optimal observation window may have closed, resulting in the loss of critical data. Furthermore, AI can miss genuine signals, particularly if they are unusual or deviate from the patterns in its training data. Machine learning systems learn from examples. By being shown thousands of asteroids, the system learns to recognize their characteristics. Similarly, exposure to thousands of comets enables it to identify their typical features. However, the system may struggle with objects that do not conform to these learned patterns. An object possessing properties outside the distribution on which the AI was trained might be flagged as noise, an artifact, or simply ignored. It could also be misclassified, placed in the wrong category, and directed down an inappropriate processing pathway. In either scenario, the signal is lost. AI can also perpetuate biases. If the training dataset is skewed towards certain types of objects, the AI's classification will reflect that bias. For instance, if the majority of training data comprises objects discovered through optical surveys in specific sky regions at particular times of year or under certain observing conditions, the AI will learn this pattern. It will associate asteroids with particular brightness ranges, colours, and motion rates. Consequently, an object that deviates from this established pattern, perhaps it is darker than usual, has a lower albedo, or moves at an unexpected speed or from an unusual direction, may not be recognized by the AI trained on the biased sample. It could be filtered out, leading the system to identify only what it was trained to recognize while overlooking everything else. Then there is the issue of noise inundation. As AI becomes more adept at detecting anomalies, it generates an increasing number of alerts. While seemingly beneficial, indicating better coverage and fewer missed objects, this proliferation of alerts necessitates more follow-up observations. Each follow-up requires telescope time, human effort, and resources. Telescopes are costly, with time on major observatories commanding thousands of dollars per hour. It is impossible to investigate every alert. Prioritization is essential, determining which objects warrant the investment of resources. If the false positive rate is high, the system becomes overwhelmed, and astronomers spend their time chasing phantom detections, potentially missing genuine threats. Achieving a balance between sensitivity and specificity is challenging. Sensitivity, the ability to detect real signals, and specificity, the ability to reject false signals, are both desirable but often inversely related. Increasing sensitivity leads to the detection of more real objects but also more false positives. Conversely, enhancing specificity reduces false positives but increases the risk of missing real objects. The optimal point, where most real threats are detected without generating an excessive number of false alarms, is narrow and constantly shifting. It is influenced by data quality, observing conditions, and the characteristics of the targets being sought, requiring continuous tuning, feedback, and human oversight. Consider a hypothetical scenario. An AI analyzing comet brightness data detects an unusual spike in the light curve of R2. The comet has been steadily increasing in brightness since its discovery, a trend consistent with rising solar heating as it approaches the Sun. Then, on October 15th, its brightness abruptly increases by approximately half a magnitude, a sharp, sudden change that deviates from the gradual increase predicted by models. This appears to be an outburst, but its timing is peculiar. The pattern does not align with previous outbursts, which typically occurred near perihelion when solar heating was at its peak. This anomaly, happening weeks later as the comet recedes from the Sun, is highly unusual. The question arises, is it a genuine phenomenon, an instrumental artifact, a tracking error, a change in atmospheric conditions, or an issue with calibration? Or is it something unexpected, a physical event such as fragment ejection, a collision with a meteoroid, or the sudden venting of volatiles? The AI, lacking an understanding of physics or models of cometary behavior, can only compare the data to previously observed patterns. Recognizing this pattern as unusual It flags the anomaly and forwards it to a human analyst. The human astronomer receives this alert among dozens of others. Upon examining the data, she observes the spike and consults other instruments to determine if any independent measurements confirm the brightness change. Her database searches yield no corroborating evidence. The spike appears solely in one dataset, which is suspicious, as artifacts are typically confined to single datasets, while real events are usually observed by multiple instruments, unless by chance only one telescope was observing at the opportune moment. She reviews the observing log for any issues encountered that night, such as telescope problems, detector malfunctions, or adverse weather. The log indicates scattered clouds and variable seeing, with no unusual circumstances noted. Examining images taken before and after the spike, the comet appears normal, with no discernible structural changes, new fragments, or significant subsequent brightening. The spike seems to have been transient, if it occurred at all. It might have been noise or a real but brief event, lasting only a few minutes and thus unconfirmed by other observers. She makes a decision. The evidence is ambiguous. While the spike could be genuine, it is more likely an artifact. Without confirmation or additional data, issuing an alert would be premature, potentially diverting resources, triggering unnecessary follow-up observations, and mobilizing other astronomers, all for an event that might ultimately prove to be nothing. Consequently, she opts not to issue an alert. The anomaly is logged in the database, marked as unconfirmed and subsequently forgotten. She moves on to the next alert. The system continues its operation, but what if the spike was indeed real? What if it indicated fragmentation, with pieces now diverging from the parent trajectory? The human decision, made under conditions of uncertainty and with incomplete data, might have overlooked something significant. Fragments take time to separate. In the initial hours or days, they remain in close proximity to the parent body, making them difficult to resolve even with high-resolution imaging. By the time they are sufficiently separated to be perceived as distinct objects, their trajectories may have diverged enough to pose individual threats. In this scenario, the AI, which detected the anomaly, is disregarded, not due to negligence on the human's part. She followed established protocols, evaluated the available evidence, and made a reasonable judgment. However, reasonable decisions made under uncertainty can sometimes prove incorrect. Over time, humans tend to become skeptical of AI alerts, because a majority of them turn out to be false positives. This phenomenon, known as alert fatigue, is well documented in fields like medical diagnostics, aviation safety, nuclear power plant operations, and increasingly astronomy. When alarms sound frequently without consequence, people gradually become less responsive, tuning them out. They develop heuristics, mental shortcuts, to filter out noise. Examples include responding only to alerts with confidence scores above 90%, following up only if multiple instruments flag the same object, or deprioritizing alerts from older telescopes known for calibration issues. While these heuristics are rational and serve to save time and focus resources on the most promising targets, they can also lead to the filtering out of genuine signals. A real threat might have a confidence score of 85%, be flagged by only one instrument if it was the only one observing at the critical moment, or originate from an older telescope that, despite its age, detected something significant. Such an alert might then be dismissed as noise. The pattern recognition that aids humans in managing information overload can inadvertently blind them to genuine anomalies. This presents the challenge of human-AI collaboration. Neither entity is perfect. AI is rapid but lacks deep understanding. It processes vast datasets in seconds, identifying patterns that would take humans hours to discern, and it never tires or loses focus. However, it lacks contextual awareness and intuition, and cannot reason about the physical plausibility of an anomaly. Humans, conversely, are slow but intelligent. They understand physics, possess intuition, and can reason about causality and likelihood. Their capacity, however, is limited by attention span, fatigue, and cognitive biases, restricting their ability to examine only a subset of the data and potentially missing events occurring outside their focus. The system functions optimally when these complementary strengths are utilized. AI handles the sheer volume of data, and humans provide the judgment. The AI scans all incoming information, flags anything unusual, and passes it to humans for assessment. Humans then scrutinize the flagged items, applying context and intuition to differentiate between real phenomena and noise. This collaborative approach necessitates trust, calibration, and feedback loops. Humans must trust that the AI is not missing critical signals, and the AI must be calibrated to provide informative rather than overwhelming alerts. Feedback mechanisms are essential, allowing humans to inform the AI of its correct or incorrect assessments, thereby enabling system learning and improvement. Furthermore, it requires humans to remain vigilant and avoid complacency, refraining from assuming the AI will detect everything. The moment humans begin to perceive AI as infallible, as a perfect detector incapable of error, the system becomes perilous. This is because AI is not infallible. It is a powerful yet limited tool that requires human oversight for proper functioning. The true danger lies not in AI's potential for failure, but in humans placing excessive trust in it and ceasing to pay attention. When human attention wanes, overlooked items multiply. Detection is no longer solely a matter of hardware, of constructing larger telescopes with superior mirrors and more sensitive detectors. It now encompasses software, algorithms, decision trees, neural networks, and statistical thresholds. It involves the rules devised to distinguish signal from noise, the models built to predict trajectories, and the pipelines constructed to process data. All of these components are created by humans, trained on data selected by humans, and deployed within contexts defined by humans. The biases, gaps, and blind spots embedded within these systems are human creations, choices, whether deliberate or unconscious, that become integrated into the systems we build. AI can enhance our observational capabilities, but it cannot resolve the fundamental issue. We are seeking patterns in a universe that is indifferent to our discoveries. The universe does not optimize for our detection efforts. It does not simplify the process for us. Objects appear from inconvenient angles, at inconvenient times, and possess inconvenient properties that do not conform to our training data. They may be obscured by the sun's glare, arrive during periods of inclement weather, or fragment unpredictably. Our detection systems, both human and artificial, must adapt to this reality to avoid failure. The challenge lies not merely in developing superior tools, but in fostering a more effective collaboration between these tools and the individuals who utilize them. Next, we will examine another neuroscience study, this one focusing on spatial memory and aging, to serve as a metaphor for how detection systems degrade over time. This is part 14, Instrument and Sensor Degradation Metaphor. Stanford's Spatial Memory and Aging Research, published on October 3, 2025, revealed findings regarding the decline of spatial memory in aging brains. Researchers investigated neurons within the hippocampus, the brain region responsible for constructing cognitive maps of an environment. These are not abstract maps. They represent our internal understanding of space and our ability to navigate within it. As individuals age, the hippocampus and its associated neural pathways can experience degradation, leading to a reduction in the fidelity and accuracy of these cognitive maps. This decline can manifest as difficulty recalling familiar routes, disorientation in new environments, and an overall diminished capacity for spatial navigation. The study by Stanford researchers highlighted how specific cellular mechanisms and network dynamics within the aging hippocampus contribute to this memory impairment. These findings offer a valuable parallel to the functioning and potential degradation of technological detection systems, such as those used in astronomy. Just as neural networks in the brain can become less efficient and reliable with age, Sensors and data processing algorithms in scientific instruments can also degrade over time. This degradation can stem from various factors: the physical aging of electronic components, the accumulation of wear and tear on mechanical parts, the obsolescence of software, or even subtle changes in environmental conditions affecting instrument performance. The consequences are gradual, often imperceptible reduction in the system's ability to accurately detect, measure, and classify phenomena. The intricate process by which the brain forms and accesses spatial memories, and how this process falters with age, provides a powerful analogy for understanding how scientific instruments, particularly those operating over extended periods or in harsh environments, can similarly lose their precision and effectiveness. This metaphorical connection underscores the importance of regular maintenance, recalibration, and an awareness of the inherent limitations and potential for degradation in any complex detection system, whether biological or technological. These are internal models of physical space, constructed from lived experiences and honed through repeated encounters. In younger creatures, these specialized nerve cells activate reliably when the organism is in a particular spot. This activation sequence is exact, consistent, and repeatable. Neuron A fires when the creature is in corner 1. Neuron B fires when it is in corner 2. This arrangement forms a mental map, a neural grid that enables the creature to ascertain its location and chart a course to its desired destination. However, in older creatures, these neurons become less dependable in their firing. Neuron A might activate in corner 1, or it could fire in corner 2, or it might remain inactive altogether. Consequently, the mental map becomes indistinct. Locations start to merge. The creature still understands it is somewhere, but the precise somewhere is lost. Navigation becomes more challenging. The creature exhibits hesitation, it retraces its steps, it makes incorrect directional choices. Eventually it does reach its objective, but the journey is inefficient, fraught with uncertainty, and marked by errors a younger creature would not commit. The research delved into the underlying cause of this degradation. Certain protein compounds accumulate with advanced age, attaching to receptors on nerve cell connections and diminishing their adaptability. Synaptic plasticity refers to the capacity of connections between neurons to strengthen or weaken based on learned experiences. It serves as the physical foundation for learning and memory. When plasticity diminishes, neurons lose their ability to update their internal maps, correct errors, or integrate new information. The outcome is a deteriorated representation of space. The map persists, but it is outdated, imprecise, and untrustworthy. The creature continues to navigate, but with reduced accuracy. It makes more blunders. Locating destinations takes longer. This decline is gradual, initially subtle, but quantifiable. Over time, it intensifies. Mistakes accumulate. The map deteriorates. This discovery extends beyond mere neuroscience. It serves as a metaphor for every observational system humanity has ever devised. Telescope systems age in precisely the same fashion. Instruments begin with exceptional sharpness, precision, and calibration, capable of detecting the faintest signals, but over time they degrade. Optical alignment shifts. The mirrors that concentrate starlight are supported by mechanical frameworks that expand and contract with thermal fluctuations. Over months and years, minute shifts accumulate. The focus softens. The image spreads out. Light that should converge on a single sensor element disperses across several. This phenomenon is described by the point spread function, a mathematical representation of how a telescope renders a point source of light, which broadens. Resolution diminishes. Mirrors gather dust. Even in the most advanced observatories, and within sealed environments, particulate matter settles on optical surfaces. Dust disperses light, reducing the quantity that reaches the detector. Even more problematic, some telescopes are exposed to the external environment. Wind carries grit. Temperature variations cause condensation. Over time, the mirror surface oxidizes. The aluminum coatings, applied to create reflective surfaces, deteriorate. Reflectivity decreases from 98% to 95%, then to 90%. Each lost percentage point signifies fewer captured photons, resulting in fainter objects being missed. Eventually, the mirror necessitates stripping and recoating, a procedure that spans weeks and incurs costs in the hundreds of thousands of dollars. Sensors develop malfunctions. Charge-coupled devices, the silicon chips that convert photons into electrical signals, sustain damage from cosmic radiation. High-energy particles impact the silicon lattice, displacing atoms and creating hot pixels that register erroneous signals. Dead pixels also emerge, areas where photons arrive but no signal is recorded. Noise patterns develop, systematic errors that must be accounted for during image processing. While the detector continues to function, its dynamic range shrinks and its sensitivity declines. Objects at the threshold of detection, those producing only a handful of photons per exposure, fall below the noise floor and effectively vanish. Calibration becomes less precise. Every telescope requires regular calibration to translate raw detector readings into meaningful measurements. This involves pointing the telescope at stars of known brightness, measuring the signal, and constructing a calibration curve. However, calibration drifts. The detector's response changes, the optical throughput fluctuates, and the Earth's atmosphere is a constant variable. Without frequent recalibration, measurements become unreliable. An object believed to be magnitude 6 might actually be magnitude 5.8 or 6.2. This uncertainty propagates, making brightness estimates less trustworthy and rendering orbital predictions that rely on brightness less accurate. The error margins widen. Images become hazier. The detection threshold rises. Objects that were previously visible, yielding clear, confident detections, now hover at the edge of statistical significance. Is that a faint comet or a random noise spike? Is it a moving object or a cosmic ray impact? The ambiguity increases, leading observers to become less certain. This necessitates follow-up observations, but telescope time is a scarce resource. If every marginal detection requires confirmation, the entire system becomes sluggish. The processing queue lengthens. Objects move out of view before they can be confirmed. We miss them. Maintenance provides some relief, but only to a degree. Mirrors can be cleaned. Dust can be removed with careful wiping or blown away with compressed air. However, cleaning introduces risks. A scratch, a smudge, or residual cleaning agent can worsen the situation. Recoating restores reflectivity, but it requires removing the mirror, transporting it to a specialized facility, enduring weeks of waiting for the process, and then reinstalling and realigning it. During this period, the telescope is inoperable. Observations cease. The survey is temporarily halted. Objects that would have been detected within that time frame are entirely missed. Sensors can be replaced. Newer charge-coupled devices offering superior quantum efficiency, lower noise, and wider dynamic range are available, but their replacement is costly. A single detector can cost millions of dollars. Installation demands precision. The detector must be cooled to cryogenic temperatures to minimize thermal noise. The cooling system requires ongoing maintenance. Leaks occur, pumps fail, systems go offline, and even with a new detector, the remaining optical components continue to age. A telescope is only as effective as its weakest element. Calibration can be redone. In principle, recalibration can occur nightly using standard stars, verifying the 0 point and measuring atmospheric extinction. In practice, cloud cover interferes, schedules slip, and automated processing pipelines may continue to use outdated calibration files. The drift goes unnoticed until someone investigates and realizes the measurements are inaccurate. By then, weeks or months of data may be compromised. Orbits calculated from this compromised data carry the error forward. leading to misidentified objects and failed predictions. However, maintenance demands resources, time, financial investment, and expertise. Budgets are finite. Funding agencies often prioritize new projects over maintaining existing ones. Once a telescope is constructed and operational, the initial excitement wanes. Headlines shift. The scientists who designed it retire. The engineers who built it move to other assignments. The institution is left with an aging system and a diminishing budget. Maintenance is postponed. Upgrades are delayed. The system degrades at a faster rate than it is repaired. Entropy ultimately prevails. The Stanford study demonstrates that even biological systems, which possess self-repair and continuous regeneration capabilities, still experience age-related decline. Neurons lose functionality despite the brain's capacity to form new synapses, eliminate unused connections, and reorganize neural networks. The hippocampus is one of the few brain regions where new neurons are generated throughout life, a process known as neurogenesis, which continues into old age. Yet even with this regenerative capacity, spatial memory declines. The newly generated neurons do not fully compensate for the accumulated damage. Synapses weaken, proteins build up, and maps become unreliable. While the degradation is slower than it would be without regeneration, it is nevertheless inevitable. Our astronomical instruments do not have this advantage. They are not self-repairing. They do not regenerate. Once damage occurs, it persists until intervention takes place. Such intervention is slow, expensive, and often incomplete. A mirror cleaned today will accumulate dust tomorrow. A sensor replaced today will develop hot pixels next year. A calibration performed today will drift next month. The degradation is relentless. The pace of decline is faster than in biological systems due to the absence of an inherent repair mechanism. And when these instruments degrade, we miss crucial detections. The discovery of Comet R2 serves as an illustration of how detection failures can occur. The comet was identified late because it was situated in a geometric blind spot, obscured by the sun's glare. However, blind spots are not always purely geometric. Sometimes they are instrumental. A faint comet at the limit of detection might be visible to a new telescope, with a recently coated mirror and an intact detector. The same comet, observed months later with the same telescope after dust accumulation and pixel degradation, might become invisible. The object itself has not changed. The telescope has. Because the telescope has degraded, the detection fails. The same object observed with the same technique yields different results depending on the instrument's condition. This is not a hypothetical problem. It is a recurring reality. Survey telescopes detect fewer objects in their later operational years compared to their earlier years. Even though the sky remains unchanged, this decline is attributed to aging hardware, degraded optics, and sensor failures. If we do not account for this, if we do not regularly test and recalibrate, if we do not meticulously track instrument performance over time, we begin to miss objects that were previously detectable. We do not realize we are missing them because they never appear in the collected data. They are essentially ghosts, unseen, undetected, and unknown. Furthermore, there is data fatigue, a distinct form of degradation. Telescopes generate immense volumes of data. Modern wide-field surveys produce petabytes annually. Each image contains millions of pixels, and each pixel holds a measurement. Processing this data necessitates sophisticated pipelines, automated software designed to identify sources, determine positions, calculate magnitudes, cross-reference information, create catalogs, and flag anomalies. These pipelines operate continuously, ingesting new data and outputting results. However, as the data volume expands, the pipelines become strained. Processing times increase, and queues form, leading to data backlogs. An image captured tonight might not be processed until tomorrow or even next week. By the time an anomaly is flagged, by the time a human examines it and deems it worthy of follow-up, the celestial object has moved. The observational window closes. we lose the opportunity to confirm its identity, refine its orbit, or assess potential risks. Data storage presents another bottleneck. Petabytes of information require substantial infrastructure, including hard drives, servers, cooling systems, and redundancy for backups. All of this incurs significant costs. When budgets are constrained, storage capacity is often reduced. Older data is archived to slower media, such as tape drives that can take hours to access. If it becomes necessary to reprocess historical images or search for a faint object that was overlooked initially, one must wait. A request is submitted, and there is a delay for the tape to be loaded, the data transferred, and the processing completed. Days pass, and by then the object of interest is long gone. Vigilance requires ongoing maintenance, not only of hardware but also of software, operational procedures, and institutional knowledge. Software contains bugs, and pipelines incorporate embedded assumptions. A threshold established 5 years ago might no longer be appropriate given changes in the sky, such as increased light pollution, the proliferation of satellite constellations, and a dramatic rise in streaks and flares within every image. The pipeline flags these as anomalies, filling the queue with false positives and burying genuine anomalies. Adjusting the threshold is not a simple matter. Modifying it too drastically can lead to missing real objects, while setting it too conservatively perpetuates the influx of false positives. Someone must monitor the pipeline, fine-tune parameters, and evaluate the results. This requires expertise, experience, and institutional knowledge. Astronomers retire, and engineers move on. The individuals who design the system, who understand its idiosyncrasies, who are aware of its blind spots, and who recall the rationale behind specific design choices, eventually depart. Documentation offers assistance, but it is never entirely comprehensive. Subtle details are lost. New personnel join the team. They learn the system, but they do not possess an intimate understanding of it. They lack the intuition that stems from years of hands-on experience. Mistakes inevitably occur. A parameter might be altered without comprehending its downstream consequences. A calibration file could be updated incorrectly. An assumption might be made that was previously challenged and rejected. The new team is unaware of the historical context. They inadvertently repeat past errors. The system drifts further from optimal performance. Detection rates decline. This goes unnoticed until someone conducts a retrospective analysis and discovers that the telescope is missing objects it should be capable of detecting. The parallel to aging brains is exact. Both systems commence with sharp precision, degrade incrementally, lose sensitivity, and fail to detect signals. Both necessitate active maintenance to mitigate their decline. Both ultimately falter despite our most dedicated efforts. The solution remains consistent: refurbish, recalibrate, upgrade, and replace aging components with new ones. Train the next generation of personnel. Document everything meticulously. Cultivate institutional memory. Combat entropy at every level, acknowledging that permanent victory is unattainable, but hoping to delay the inevitable long enough to make a meaningful impact. The Stanford researchers demonstrated that inhibiting age-related proteins in mice restored some aspects of spatial memory function. This intervention did not rejuvenate old mice, rather it mitigated their oldness. It slowed the decline and bought valuable time. This is precisely what maintenance accomplishes for telescopes. It does not restore them to their original factory condition, but rather decelerates their degradation and acquires time. Time sufficient to detect the next R2, the next unexpected visitor, the next object concealed within the glare or lurking at the edge of sensitivity. Time is the most critical resource. When systems fail, when detection lapses, when degradation triumphs, we lose time. And losing time means forfeiting the opportunity to perceive approaching threats before they arrive. Next, we will conclude our discussion. We will explore what lies ahead, what you should observe, what you should advocate for, and how all of this connects to Apophis, the asteroid known to be approaching in the year 2029. Part 15, Global Summary, What to Watch Next, and Mission Roadmap. If R2 serves as a wake-up call, here is our path forward. The comet will make its closest approach on October 20th, 2025, at a distance of 0.26 astronomical units. This is a mere 8 days away. Between now and then, the following actions are imperative. First, ephemeris updates are essential. The trajectory must be continuously tracked, the orbit refined, and perturbations closely monitored. Outgassing generates non-gravitational forces. If the comet experiences another outburst or vents material asymmetrically, its trajectory will shift. While the shift may be minor, it could be significant enough to matter. Continuous measurement and refinement are crucial. We must not assume the current orbital solution is final. Second, spectroscopic and radar observations are vital. We need to ascertain the composition of R2. Spectroscopy reveals the composition of the coma, identifying the gases being released and the molecules present. Radar, provided the comet comes sufficiently close and the appropriate dishes are directed at it, can resolve the nucleus, measure its dimensions, detect its rotation, and potentially reveal its internal structure. This pursuit extends beyond mere scientific curiosity. Composition directly influences the comet's behavior. Nuclei rich in volatile substances are more prone to outbursts. Structure impacts the risk of fragmentation. If the nucleus is a loosely bound collection of chunks held together by weak gravitational forces, it could disintegrate. Conversely, if it is a solid monolith, it will remain intact. We must determine which scenario applies. Third, high-resolution imaging is required. Efforts should be made to resolve the nucleus and detect any fragments. If R2 is fractured with pieces dispersing, we need to observe them now, while there is still ample time to track their trajectories. Fragments diverge slowly initially. The sooner we identify them, the more accurately we can predict their future paths. Fourth, monitoring for dust and debris is necessary. Look for trails, ejection events, and meteoroid activity. Earth-based meteor cameras can detect particles entering the atmosphere. Satellite sensors can measure micrometeoroid flux. If R2 is shedding debris and Earth is approaching a debris stream, we need advance warning. Even a few hours of warning is sufficient to place satellites in protective modes, orienting solar panels edge-on to minimize their cross-sectional area. Fifth, spacecraft hazard modeling is essential. The International Space Station orbits at an altitude of approximately 400 kilometers. Satellites occupy various altitudes, from low Earth orbit up to geostationary orbit at 36,000 kilometers. All of them are potential targets. A dense meteoroid stream increases collision risk. While the risk remains low, low is a relative term. If the background flux is 1 particle per million cubic kilometers per hour, and a debris stream elevates it to 10 particles per million cubic kilometers per hour, that represents a 10-fold increase. Small numbers multiplied by vast volumes and extended exposure times accumulate. Modelling the flux allows us to estimate the risk and prepare contingency plans. Now, regarding policy and systems, what should we demand from the institutions responsible for our protection? First, increased investment in solar ward surveillance is paramount. Most of our telescopes are directed away from the Sun, a natural inclination due to its overwhelming brightness, which can blind sensors. However, objects approaching from the Sun's direction remain invisible until they emerge from its glare. We need space-based telescopes strategically positioned to observe the Sun, instruments capable of detecting comets and asteroids within the Sun's blinding light. The SOHO SWAN mission demonstrated the efficacy of this approach. We require more instruments like it, dedicated to comet detection across a broader spectrum. Second, real-time public data pipelines are crucial. Transparency helps to fill the void left by speculation. When observations are published immediately, when orbital solutions are updated in real time, and when uncertainties are communicated clearly, public trust increases. People do not need to resort to conjecture when the data is readily accessible. The Minor Planet Center and JPL already provide some of this, but their interfaces are highly technical. We need public-facing dashboards, visualizations, and summaries presented in plain language. The data must be made accessible and understandable. Third, international coordination is vital. Telescopes are distributed globally, each operating in different time zones, covering different sky sectors, and possessing varied capabilities. A network coordinated in real time can provide continuous tracking of objects. When one telescope loses sight of an object as it dips below the horizon, another can pick it up. Alert protocols need to be standardized. If one observatory detects a potential hazard, how rapidly is that information disseminated to other observatories? How quickly does it reach decision makers? Minutes matter, hours matter, and days matter. Let us consider Apophis for contrast. Asteroid 99942. Apophis, with a diameter of approximately 340 meters, will pass closer than geostationary satellites on April 13th, 2029. This is less than 4 years away. We have known about Apophis since 2004. We have tracked it for 21 years. We know its orbit with extreme precision. We know its exact location on April 13th, 2029, to within a kilometre. We are certain it will not impact Earth. It will pass at a distance of approximately 31,000 kilometres, closer than some satellites, but still a safe margin. We have sufficient time to prepare, to position instruments, and to study it during its close approach. Apophis represents the predictable scenario, the one we anticipated and can observe in slow motion. R2 is its opposite, unpredictable, detected late, with an uncertain orbit, unknown composition, and the potential for fragmentation. R2 is the type of event that causes consternation among risk analysts, not because it poses a direct impact threat, but because we almost fail to detect it. And there are others like it, others we have not seen, others we will not discover until it is too late. The crucial difference between Apophis and R2 is time. Apophis provided us with decades of warning. R2 gave us weeks. Time is the most valuable resource in cosmic defense. It allows for observation, for trajectory refinement, for evaluation of options, and for decisive action. When time runs out, our options dwindle. We are left observing, hoping, and praying that the calculations hold true, that the uncertainties do not swing unfavourably, and that any fragments do not diverge into Earth-crossing trajectories. Predictable large objects garner attention. Apophis will be exhaustively studied. Every telescope will be directed towards it, and every radar system will ping it. We will learn more about asteroids during a single flyby than we have in decades of distant observation. This is beneficial. The true peril arises from the celestial bodies we fail to anticipate. These are the minuscule, swift, and unexpected entities, the profound enigmas that elude our notice, veiled by brilliance or appearing from unforeseen vectors, suddenly illuminated after our gaze has shifted. It is these that will inevitably catch us unprepared. The cosmos harbours no intent to extinguish us, nor does it aim to preserve us. Its disposition is one of utter impartiality. Celestial objects traverse the void, governed by the immutable laws of gravity and momentum. Occasionally their trajectories intersect with ours. While the majority deviate, some will inevitably make contact. This phenomenon follows a statistical pattern, appearing random over brief periods but becoming predictable across vast epochs. We are fortunate to exist within a fleeting epoch where such collisions are sufficiently infrequent to permit the flourishing of civilization, yet occur often enough to necessitate constant vigilance. The colossal asteroid that precipitated the demise of the dinosaurs impacted Earth 66 million years ago, measuring 10 kilometers in diameter, hurtling at 20 kilometers per second, and unleashing an energy comparable to billions of nuclear detonations. This cataclysm carved a crater 200 kilometers wide, propelled debris into the stratosphere, plunged the world into darkness, and brought an epoch to a definitive close. Such an eventuality could transpire once more. Not imminently, perhaps not within our lifetimes, but it remains a possibility. The critical question is whether we will possess the foresight to detect it. Will we have sufficient time to implement countermeasures? Will we have established the requisite infrastructure, cultivated the necessary technologies, trained dedicated personnel, and forged collaborative international bodies capable of orchestrating a defense? Or will we, like the dinosaurs, remain oblivious until the very heavens ignite? The object designated R2 will not be that harbinger of doom. It is too diminutive, too distant, and its trajectory is too precisely mapped. However, it serves as a crucial trial. It is a test of our detection capabilities, a gauge of our communication networks, and an assessment of our capacity to confront unforeseen circumstances with reasoned action rather than succumbing to panic. To date, our performance has been commendable. The celestial visitor is under constant observation. Its orbital path is being meticulously refined, and the associated risks are being openly communicated. There is no widespread alarm, nor should there be. Nevertheless, our focus should not be diverted by sensationalism, sensational headlines, speculative theories, pronouncements of doom, or exaggerated claims. Instead, we must direct our attention to the shortcomings, the blind spots, the failures in detection, the bureaucratic impediments, and those aspects we overlook due to misdirected observation, inopportune timing, or inadequate instrumentation. These are the true learning opportunities, the elements of genuine consequence. Observe the heavens, advocate for enhanced observational systems, scrutinize prevailing narratives, cultivate a spirit of inquiry and maintain a healthy dose of skepticism. The universe teems with both marvels and dangers. For the most part, the wonders can be appreciated without peril. However, the hazards do not herald their arrival. They do not solicit permission. They simply materialize. And when they do, the sole bulwark between humanity and oblivion is the efficacy of our detection mechanisms and the swiftness of our response. 8 days remain until the closest approach. R2 is nearing. We are observing its progress. Statistical projections indicate a negligible risk, but numerical estimates are not absolute certainties. Probabilities, often cloaked in mathematical formulations, can occasionally defy expectations. This is precisely why we maintain our watch, why we meticulously calculate, why we invest in telescopic technology, train dedicated astronomers, fund extensive surveys, and foster global cooperation. Because the alternative, ignorance, is a far greater peril than the objects themselves. The cosmos is not a void. It is densely populated with fragments, remnants, transient visitors, and wandering bodies. The majority traverse our path without incident. Some do not. R2 serves as a potent reminder that our celestial neighbourhood is not quiescent, that interstellar traffic is a tangible reality, that the risk, while presently minor, is never truly zero, and that a state of perpetual awareness is not paranoia, but an essential component of survival. Continue your observations.